Assalamu alaikum. So this is part 2 of lecture 4. In this lecture we will try to understand about TTL logic family, transistor logic family. So to understand that, first of all we will try to understand a concept of a particular device which is called multimeter transistor. So what is multimeter transistor? Basically, the figure you can see here is an example of multimeter transistor. So here you can see we have it looks generally like transistor. It has one base and one collector, but it has three different terminals for emitter. So E1, E2, and E3. So if you want to structurally understand internally how it works, the architecture, so it is basically just like connecting three transistor like this. Okay, so here we have three BJTs connected in such a way so that all the collectors of all three transistors are connected together, all three bases are connected together, but emitters are actually separate. That's how we get this kind of multimeter transistors. The number of emitters can be 3, 4 as per your requirement. Okay, so this is required because for the architecture of TTL we will see that uh, inside of this architecture at the input side we will use this kind of multimeter transistors. And one question there can be, like in the classes as well, I asked you this question whenever I covered this topic, why we use this kind of multimeter transistors instead of this kind of separate three transistors. We can do that. We can, if we want, we can use this kind of separate three transistors just connected in this way, so that it behaves like that and it will exactly work just like this multimeter transistor without any issue. But still we use this kind of devices. Fabrications are done in such a way so that we can get this kind of behavior. So why is that? My question was why we use this kind of configuration. So you should figure it out yourself through self study. So next, if we understand that, I mean multimeter transistor, I think I still should cover one thing before we move on to that. So the idea of multimeter transistor is that in general, whenever in any transistor we have one base to emitter path junction, right? If that becomes forward bias, that means if the base of that transistor is 0.7 volt higher than that emitter, then that particular junction is forward biased and that device becomes active, right? Here in this case, because we have three different junctions here from base to three different emitters, that means if any one of these three junctions can be forward biased through the application of voltage, then this whole device will become active. That is the idea, because in one of the three paths the current will flow in that case because of active or in saturation mode, right? So that's how it works. So now how that actually works in terms of our circuit, which is TTL logic family, we will try to understand that through the help of this circuit, which is an implementation of TTL NAND gate. So before we do that, let us try to compare the circuit we have here for TTL with the one we have already learned before. So this is one example of what DTL NAND gate, right? DTL NAND gate. So how that relates to the circuit we have here and why we have modified the circuit we had from DTL to this version, we will try to understand. So first of all, if you look at these three particular paths we have, the junctions we have, which is quite similar to the three diodes we had earlier in DTL, right? So basically the three paths we had connected to the three inputs. Similarly here we have three different junctions, and for these junctions as well the forward voltage drop is 0.7, just like the diode here, right? So we are replacing this diode with these three junctions, multimeter junctions, right? Then if we look at D1 we had in DTL, similarly we have this junction, this base to emitter junction, sorry, this base to collector junction of Q1 is replacing D1 here. Similarly here we were going to see similar kind of voltage drop, and for D2 you can see we have this junction here. For Q2 of Q2 from base to emitter, this junction is replacing D2 of DTL. This is how we are modifying the circuit, and why we are doing that, through the explanation of different cases, we will finally understand how this particular architecture is an improvement of the one we had earlier, DTL, right? So let us start. So now we will try to understand case by case how it actually works. Okay, so just like before, so in the previous DTL example as well, because that was an AND gate of 3 inputs, we know that for those cases we have how many possible inputs? A, B, C, and output is Y, right? So that means 8 possible conditions, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0. In this way, up to 1, 1, 1, right? And we know for NAND gate, the output should be something like whenever all the inputs are 1, then we get at the output 0, logic 0, right? Because this is just like inverse of AND. And for all other cases, if at least one of the input is 0, that will cause the output to be 1, right? So all of them will be basically 1, something like that. So this is the truth table. So for our case, just like DTL, we are going to see that for the condition whenever at least one of the inputs is logic low, which is from starting from here up to this portion, right? All of these 7 conditions, we are going to see similar behavior. So case 1, and for the last case, case 2, whenever all the inputs are high, then we are going to see output as 0. This will be another case. So in these 2 cases, we will try to explain our circuit. Okay, so if at least one of the inputs is 0, let us take one example of that. Like we know that whenever we say in this kind of circuits logic low, that is in terms of output is 0.2, right? 0.2, and whenever we say output is high, the voltage is 5, because this depends upon this output transistor. Whenever we are in saturation, the voltage from collector to emitter, or you can also say ground, is actually 0.2 volt. So that is the low voltage and logic low condition. And whenever this is cut off, we directly get voltage from this supply voltage 5 volt, and there will be no voltage drop here. We saw that in DTL, we saw that if you remember, and because of that we got 5 volt, which was logic 1 or logic high. So in any case, the possible outputs we can get from this kind of devices are either 0.2 volt for logic low and 5 volt for logic high. So if similar kind of circuits are connected with the inputs here, so we can expect the similar kind of behavior. So we can assume that maybe similar kind of gates are connected with input A, input B, and input C. So A, B, C can also expect either 0.2 volt or 5 volt corresponding to logic 0 or logic 1, right? So this is what we are going to do. So if that is the case, basically let us take one condition like that. So let's say maybe A is getting low signal, so 0.2, B is getting high, so 5, and C is getting high, so 5. In that condition, what will happen? Because we are getting 0.2 here and this particular junction here, right? This particular junction, which is corresponding to this 0.2 voltage at the emitter, will be forward biased because we have enough voltage to provide through this path, right? So this P node will be in a such a value so that this particular junction will be forward biased. But if I talk about the next two inputs B and C, they are getting 5 volt, and these two junctions will not be forward biased because P cannot provide 0.7 volt higher than that voltage, which is 5.7. At most what we are getting is 5 volt. So never this junction and this junction, the B and C, these paths will never be turned on because we are not getting the voltage we need for that. Okay, so still, as we said, if at least one of the junction is forward bias, that will be enough to make this device turned on, right? So that is the case. So we will see, because of this junction, the first junction, the device is forward biased, and at P the voltage we are going to get is we can say something like that. Vp should be equal to what? 0.2 plus 0.7, the voltage required for forward biasing that junction is equal to 0.9 volt, right? So this value will be 0.9 volt. Now the issue is, if I want this particular path to be turned on, basically if any current should flow in this path, then this junction here, the base to collector junction of Q1 or base to emitter junction of Q2 or base to emitter junction of Q3, all of them has to be turned on or forward biased for that to happen. And all three things has to happen at the same time. All the three things has to happen together. So that means if that should happen, the minimum amount of required voltage we need is 0.7 for this case, 0.7 for this case, and 0.7 for this case, right? So one thing you may ask, like, why from base to collector voltage here should be 0.7, right? You may ask. So same question I asked in the class, and I asked you to investigate. Like, we know that for the similar kind of transistors, whenever a particular transistor is, let's say I just draw that something like that, and we have a resistor like that, maybe that is connected to a voltage 5 volt, and here we have, maybe we can have a resistor, no problem with that, but this is the base, right? And this is the collector, and this is the emitter, right? Now the thing is, we know that whenever this base to emitter junction has to be forward biased, the voltage required is 0.7, right? And after that, the device goes into active mode, and if we keep increasing the voltage at the base, what happens? The IB current, the base current increases, so does the collector current, and as a result, if the collector current increases, the resistance drop here increases, which reduces the collector voltage. And we see that in such a moment, previously this particular junction from base to collector was reverse bias, because this is at a higher voltage and compared to base. That was the situation, and we have discussed these things over and over again before the meet in different classes, so you should understand. So we saw that whenever this voltage drop increases, reducing the collector voltage here, at certain moment this particular junction also becomes forward bias, so the voltage at this node becomes higher than this, but the voltage required was something like 0.5, if you remember. Okay, so if collector can be 0.5 volt lower than base, that will be enough to make this particular junction forward biased. But if we look at this junction from base to emitter, this was 0.7. So why this difference? I mean, both of them are similar kind of junctions, similar kind of like your diodes, but still the voltage required is different. The reason for that I explained was because of the way they are doped. The emitter is doped, highly doped, but collector is not highly doped. As a result, the voltage required for being forward biased was not same, right? This is partially true, not wrong, but you see here, like in this case, we are looking at a condition whenever we want this particular junction to be forward biased, right? So in that case, we will see that later on, I mean like in the next case, we will see that whenever we will find this particular junction to be forward biased, the voltage we will require will be 0.7, okay, not 0.5. And we will also see that at that moment this particular junction is not forward biased, so we call that situation reverse active mode. In active mode, what we see, base to emitter junction is forward biased, but base to collector junction is reverse biased. That was the condition of active mode. In reverse active mode, we are going to see that this base to collector junction will be forward biased, but base to emitter junction will not be forward biased, rather reverse biased. This will be the condition, and that's why we call that reverse active. And in that condition, the voltage required will be 0.7 from base to collector for this junction to be forward biased. And we are going to take the same assumption here whenever we will say that if the path here from here to here to here, or if the whole path needs to be turned on, or if current can flow through that path, this this particular junction needs to be forward biased, and the voltage required will be 0.7, not 0.5. So again, I will request you to investigate why is that. Why for the same junction, for two different modes, the voltage required is different. Okay, so I think I can remove that now. So you see, the voltage required is what we can say, that is VBC of Q1, right? Q1 plus VBE of Q2 plus VBE of Q3. We are just talking about turning on, not still saturation. So we need 0.7 here plus 0.7 here and plus 0.7 here at least. So at least 2.1 volt is required at VP. I mean at this point at P we need, which we don't have. That means all of the junctions here will be reverse biased and we will get no current here. Q2 will be cut off, Q3 will be cut off. So if Q3 is cut off, what is the condition? So this is open circuited, that means no current should flow through here. That means the 5 volt we are getting here will go through this path, and because Y is still not connected with anything, we can assume that no current should be flowing through here, and the resistance voltage drop here can be considered 0. So we will get directly 5 volt at the output whenever we get at least one of the inputs as logic 0 or corresponding voltage, that is 0.2 volt. Okay, so this is true for all 7 conditions whenever at least one of the inputs is logic 0. Okay, so now let us look at the next case whenever all the inputs are logic high. So we are talking about a condition whenever A is getting 5 volt, B is getting 5 volt, C is getting 5 volt. This is where we will get the reverse active mode. So you see, if all of the inputs are 5 volt, that means none of the junctions here can be forward biased because we don't have 5.7 volt at P node, because we are providing 5 volt. We cannot get higher than that. So as a result, what we will see is that all of the junctions are reverse biased, and you can basically practically think of this portion as disconnected from the circuit. So nothing will go through there. And now this P node is independent. It can move up to any positive voltage so that it can provide for Q1, this junction, and this junction, and this junction. Okay, so let us look at the maximum condition. So the best condition we can get, and what is the required voltage for that. So what I mean by best condition, so Q1, if it is forward biased, we need at least 0.7 volt. Okay, and if that happens, from base to collector this junction is forward biased, but from base to emitter this junction is reverse biased. So that means this particular transistor Q1 is currently now in reverse active mode. That's why 0.7 volt here is required. And then here we are going to take one assumption such that we said, like you remember that VBE on was a term. So whenever a particular transistor is turned on, then from base to emitter voltage required is 0.7, we know. There is another term called VBE set, which is saturation. So whenever a particular transistor is in saturation, then for the transistor from base to emitter, what is the voltage required? Up until now, the value we have used for this case was also 0.7. So we just simplified our explanation such that whenever it's in active mode, a transistor is in active mode or in saturation, in both of the cases the voltage from base to emitter required is 0.7. So now, to make it a little bit more accurate, what we want to do is we want to say the voltage for saturation, I mean base to emitter voltage, should be 0.8, slightly higher than that, because whenever we are talking about saturation and active mode, obviously in saturation mode the base current is higher than the one we got for active mode. You have to understand, because from active mode, as we increase the base current, so does collector current, and that actually forces us into the saturation mode, right? So we also know that if the base current increases, that obviously will also flow through the base to emitter junction, which is a diode. We know that in a diode, if you can increase the voltage across a diode, current should increase. There is a relationship like that, right? Something like that. So basically this was the voltage, this was the current. So even though not linear, but still, if current increases, even if slightly, voltage will increase. So maybe we get here 0.7, and maybe here we get 0.8. So you understand, still there will be slight change of voltage as we increase the current. So that's why we are saying whenever we are in saturation, because the base current is much higher, the voltage required for that condition should be slightly higher than the one we got for active, which is 0.8. So from now on, if we have given in the exam, this kind of assumptions are already given, you have to use that to your calculation. But if written both of the things are given as 0.7, then you can use for both of the cases saturation and active 0.7, no problem. But here for this explanation we are going to take this assumption. So if that is the case, let us try to understand. So we said that if this particular junction needs to be forward biased, then this particular junction base to emitter is at a voltage so that this transistor is in saturation, so which is 0.8. And also similarly, if I want Q3 to be in saturation, then from base to emitter voltage should be 0.8. So kind of like I can write that. I think I can write it like this: VBC Q1, Q1, then VBE set of Q2, then VBE set of Q3. So all of them together, right? What should be the value? So this value should be 0.7, this value is 0.8, and this value is also 0.8. So in total it should be what? 2.3 volt, right? So we need at least 2.3 volt here for all of the things to turn on and be in saturation, and we can get 2.3 volt here because we have 5 volt. So 5 minus 2.3 divided by the resistance will be the current flowing through the base, and we are going to get 2.3 volt. So as a result, This is in reverse active mode, this is in saturation, this particular transistor is in saturation, and Q3 is also in saturation. And we know if a particular transistor is in saturation, what is the voltage difference from collector to emitter? That is 0.2, from our earlier explanation about transistors in saturation, right? So what we are going to get is 0.2 volt at this condition. So whenever all the inputs are high, 5 volt, then output should be 0.2 volt. Okay, now we will try to understand why TTL is better than DTL. Okay, so to understand that, first of all, we have to understand what is storage time here. Okay, so what is storage time? Storage time is the delay that occurs when you try to turn off a bipolar transistor that has been driven into saturation. Okay, so you are already in saturation, and whenever you want to turn it off, there will be some delay. The delay, the reason of that delay is because try to understand, like, if I draw a particular transistor, NPN transistor, just so that it is easier to understand. So it is something like this: N, P, N. So P is connected, basically base, this N is emitter, and this one is collector, right? And whenever we say this particular transistor is in saturation, that means from collector to emitter a high amount of current is flowing, or if I want to take the convention of electron, that direction will be what? From bottom to top, something like that. Electron, right? So high amount of electron is flowing from emitter to base, then to collector in this way. So basically these electrons are majority carriers of N region, no problem, and also majority carriers of N region here for collector, but minority carrier for the base. And this is kind of like a hostile environment for those electrons because they are minority carriers there. Understand? So suddenly, whenever you let's say you are in saturation, then suddenly you just turn off the base current. What happens? Some of the electrons get, trapped in this P region, and as this is a hostile region, it cannot just move away. It has to diminish in some way. So how it gets diminished is through recombination. Okay, so it has to flow somewhere, either to the collector or maybe here through the recombination of holes and electron. It happens, but it will obviously take some time, and that amount of time we still see that our transistor are still behaving as if it is in saturation. Okay, so that is the delay we are talking. So ideally what we want, whenever a transistor is in saturation and we suddenly just turn off the base, at that moment exactly the current flow should also stop, but that doesn't happen. It takes some time. So how can we actually solve that issue? Because it can obviously cause problem for our circuits, right? It can actually introduce delays into our circuit. So this problem we also saw in our DTL example. And if you remember, like for DTL, we saw that this particular resistor here through the ground, we deliberately use that so that whenever this situation happens, whenever if this transistor was in saturation, then suddenly base current is gone to zero, then obviously there will be some charge stored at the base, and how we have to somehow dissipate that so that quickly we can transit into another state. So that was done through this path. Extra charges were dropped through, or going through this path through the resistor. That was the idea, but obviously that was not a very good solution for this issue, and still it takes some time to dissipate that. And we also saw that the trade-offs of selecting the value of that resistor, higher or lower value, how that affects the circuit. So now in TTL, what we will see is that we have using this kind of multi-emitter transistor, we have automatically invented a way to discharge those charges, or move those charges from the circuit or from the transistor, so that this transition can happen quicker. So how is that? Let us try to understand. So let's say uh, in a situation all of the inputs are actually high, 5 volt, 5 volt and 5 volt, okay, and as a result what will happen, these junctions are reverse bias, we will get at P the voltage required for these whole paths to be turned on, so which is what, 0.7 plus 0.8 plus 0.8, so P will be at 2.3, right? And as a result, at the output the voltage we are getting is 0.2 volt, because this Q3 is now in saturation. Now suddenly if you just change one of the inputs, let's say this one, to 0.2, what will happen? Because of this 0.2, this particular junction will be forward biased, and which will reduce this node voltage of P to 0.9, right? So if that happens, if this is 0.9 volt, then obviously now we don't have enough voltages to provide for this junction or this junction or this junction, right? So this particular Q2 was in saturation, try to understand. So now the base has extra charges stored, so how can it actually move from there to somewhere, so that transition can happen quickly? The idea is, if you want to calculate the voltage here, what is the voltage, you have to come from here, right? So still, because all of the junctions are still behaving like saturated, it cannot just deliberately at instant go to cutoff mode. Still we can say the voltage we are getting is 0.8, and also the voltage we are getting is 0.8. As a result, the voltage here is what, 1.6 volt, right? And 1.6 volt is obviously higher than the voltage we have at base, so this particular junction is currently now in reverse biased mode. And this for this AMET, one of the junction is forward biased, so base to emitter junction is forward biased. So this is currently now in active mode. In active mode, from collector to emitter current can flow. So what will happen, whatever extra charge is actually stored here can push through here through this path, understand? So something like this, it will go outside. So that is how quickly the extra stored charges can dissipate here in this circuit. Here, one thing I should mention, that even though we say that this current here is pulling all the charges from Q2 and Q3, even though that is true for Q2, but Q3 is not directly tied to the Q1. So what happens is, basically because of this large collector current going through Q1, Q2 is getting turned off very quickly, so it is not providing any current through Q3 at all. So as a result, whatever charge is stored here can be quickly dissipated through this resistor. But you can also see the resistance value here, which is quite lower compared to the one we saw for DTL. So here we can use that because of the circuit configuration. As a result, the overall configuration switches much faster compared to DTL. Now, clamping diode. So you have seen this kind of portion, 3 diodes connected with the inputs, but whenever we explain the functionality of the circuit, these portions were never discussed. So these are not functional parts of the circuit, but they are useful for safety measure, basically. So using this kind of diodes, what happens is the input values cannot go lower than a certain value. So basically the idea is, let's say if for a particular input, if the value goes through, let's say like -3 volt, then what will happen, because the anodes of this diode, this particular diode is connected to the ground, so here the voltage we are getting is 0 volt. So at this node the voltage we should be getting is what, 0.7 lower than that, so minus 0.7 we are going to get. So which will force this minus 3 voltage to this value, so that the inputs cannot go lower than that minus 0.7 volt. Why is this necessary? Because if the input voltage goes very low, that means what? If this is minus 3 volt, then P will be just 0.7 volt higher than that. So at that moment, P should be what? P should be equal to minus 2.3 volt. Now look at this circuit. The current that will go through this path will be what? This voltage minus this voltage divided by this resistance. If this value is much lower, that means obviously the current will be very high, which may damage this particular transistor. That is the thing. Base current if goes very high, that can damage the circuit. That's why we need this kind of protection diodes. These are called clamping diodes. Okay. Now we will look at one math problem. So basically just find out some amount of current here. Okay. So they're saying if A, B, C, all of them are 5 volts. So basically something like this, 5, 5 and 5. Then what should be the current going through this path, which is what? Emitter current of Q3. For this Q3, what is the current going through the emitter? We have to find that out. Okay. So how can we start? We have to take some assumptions, like as we said, we are going to take something like that. VBE set will be equal to 0.8 volt. This is the assumptions we are going to take, and in the exam as well these values will be mentioned. And let's say VBE set is equal to 0.2, which we always have used, right? Then VBE on, just for making a transistor active, the base to emitter voltage is 0.7. These are the three things already given to us, let's say. Okay, so then how we can solve that? Okay, now first of all, we are going to try to understand in what configuration they are in, right? So basically all of them are getting 5 volts, so obviously all of the junctions here are reverse biased. So P will be at a voltage which is needed for this to be forward bias, this to be in saturation, and this to be in saturation. So 0.7 here, 0.8 here, and 0.8 here, right? So basically we can say Vp should be equal to what? VB C Q1 plus VBE Q2, you can write in bracket saturation, and then VBE Q3 saturation. So this is the voltage, and which is 0.7 plus 0.8 plus 0.8. So in total 2.3 volt, right? Vp, this voltage is 2.3 volt. Then we can also find out the current going through this path. Let us call that what? IB1. So IB1 is equal to what? IB1 is equal to this voltage minus this voltage divided by this resistance. So 5 minus 2.3 divided by 4K. So that value is equal to what? It comes out as 0.675 milliampere. Okay. Then we can also say that the current that is going through this path is never going to go to this path, because this is disconnected now, reverse bias. So all the currents IB1 will go through this path, which can be actually considered as what? Current going through base of Q2, IB2. So this is equal to IB2, right? Then our goal is to get here somehow, right? So for that we need this current, this current, this current, all of the currents are actually needed. So one by one we will try to find out. So let us try to find out the current that is coming from here. So let us call that what? IC2. So IC2 is equal to what? To find that out, first of all, you need to find out what is the voltage we get here, right? So we know that this particular transistor is in saturation. So from collector to emitter, the voltage we should get is 0.2, right? So from here to here 0.2, then also we can come here, and from here, from this point to this point, the voltage is what? 0.8, because this transistor is also in saturation. So for Q3, from base to emitter, voltage is this one, right? So 0.8 here and 0.2 here. So I can just write that out. 0.2 from here to here, and then from here to here we have 0.8. I'm just removing that because it will just making everything complicated. So we should just know that the voltage we are going to get here at this node is 1 volt. So that means the current IC2 should be what? 5 minus 1 divided by this resistance. So 5 minus 1 divided by the resistance, which is 1.4 K. This value comes out as 2.86 milliampere. Okay. Then what? Then we can find out the current that is coming out of the emitter. Try to understand. The current that is going through this path through Rx is not equal to the emitter current of Q2, because the emitter current of Q2 is getting divided into two branches. One going through this path, let us call that Ix, and another one is going through this path, let us call that base current of Q3 or IB3. Okay, so what we are trying to find out is the current here coming out of emitter of Q2. So basically IE2. So IE2, from the very simple equation, IE is equal to emitter current is equal to base current of and collector current, summation of those. So IB2 plus IC2. So you have to just add these two, right? Because IB2 is this one, IC2 is this one. So if you add these two up, you are going to get what? 0.675 plus 2.86 is equal to 3.53 milliampere, right? So okay, now let us go on to next page. So now what we know the current I3, right? This is actually, I don't know how to write that here. Let us write it here, IE2. And can we find out the value of IB2? This is what we need. So for that we also need this value Ix. So what is Ix? What is the value at this point? Voltage of this point is equal to 0.8. We already discussed that, because this is forward biased and in saturation. So at this point the value should be 0.8. So Ix should be what? Ix should be the voltage 0.8 divided by 1K. So that value is what? 0.8 milliampere. Now we can say that the current here is equal to this current minus this current. So IB2 is equal to IE2 minus Ix, which is equal to IE2 is equal to what? We found out that this IE2 was 3.53 minus Ix 0.8. So we get what? 2.73 milliampere as IB2 current. Now we only need this current which is IC3, right? If we can find IC3, these two current together, sorry, it should be actually IB3, not IB2. Okay, so this is IB3. So if I can find IC3, then addition of these two current should be equal to the emitter current of Q3. So IC3 is equal to what? IC3 is equal to the voltage here minus the voltage at Y. We know this particular transistor currently is in saturation, so Y is equal to 0.2. So if that is the case, then 5 minus 0.2 divided by the resistance we have, which is 4K, is equal to what? 1.2 milliampere. Right? From that we can find out the current that is required to be found out here in this question. IE3 should be equal to IB3 plus IC3. So IB3 is equal to what? 2.73 and IC3 is equal to 1.2. So in total what? In total we get 3.93 milliampere. So this is the result of the current required in the example. Now the circuit we have so far learned for TTL, we will try to make some improvement on that. So to understand that, first of all we need to understand the issue we have that we are trying to solve in the circuit. So load capacitance, what is that? So load capacitance is the total capacitance that the output of a logic gate must charge or discharge during a logic transition. So output of the logic gate. So we will try to look at the circuit itself, but try to understand why this happens. Like for example, if I look at this circuit, the same circuit, right? So we know that this kind of gates are cascaded together. That means similar kind of circuits can be connected with input of A, input of B, or input of C, right? If that happens, so for that particular gate at the previous stage, this A is connected with the output, right? So this particular junction here, you know, whenever reverse bias, this actually acts like a capacitor. How is that? For a capacitor, we know that, you know, the required thing is you need to have two conductors, and in between that we need to have an insulating material, right? So whenever we have a particular junction, PN junction, you know, in reverse bias condition, something like that, if that is reverse bias, already we will have a depletion region created here, and that will act like a insulating region, and we have the conducting plates here, right? So it basically acts like a small capacitor. So in those cases, basically at the output we can assume that a capacitor is actually connected. And the problem with capacitors is that the voltage across a capacitor cannot abruptly change. Okay, so that is the thing we have learned in previous semesters. So let's say if I have a circuit, where can I draw that? I think I can draw it here. So if I have a circuit like that, you know, maybe we have a voltage source here and we have a resistor connected like that. So maybe Vs is the voltage, that can be 5 volt or something. This is a resistance. So if that voltage is changing like that, let's say, so high and low, then in this way, if this is changing, let's say this is 5 volt. If I want to draw the voltage across the resistance, which is VR, VR will behave similarly. Maybe the amplitude can be different, but VR will basically will take the same shape. Okay, something like that. That is the idea. So as soon as you change the supply voltage from high to low, instantly resistance also behaves or responds to that without any kind of delay. But what if this thing we have drawn here is not actually resistance, rather it's a capacitor? If that is the situation, what will happen? Let us call that VC. Then obviously these voltages changes of Vs will not reflect to the output instantaneously. It will take some time. So you will see that it will take some time. What can I use to draw here? Maybe I can use this color. So something like this. Whenever the input is going from high to low, it will take some time. Okay, it will take some time like that. And then again, whenever it goes from low to high, the capacitor voltage will change like that. It will take some time to go there. It will take some delay because the voltage across a capacitor cannot change abruptly. So similar kind of situation will also be seen for our circuits, because we are saying that this kind of capacitance, load capacitance behavior can be seen in circuits at the output. So we will see that we will use this kind of capacitors to represent that output capacitance or load capacitance. So here also written whatever I have discussed, like the junctions of the transistors can act like small capacitors, which are coming from multimeter transistors. And also sometimes whenever you have this circuit, these are printed on PCBs, adjacent wire together, very close wires together, traces together, can introduce capacitance, because they are also like similar type of thing. Two conductors separated with some distance, there can be some insulating material or there can be just air. So still they can act like capacitance, and they can behave how capacitors generally behave. So that's the problem, because whenever what we want from this kind of circuits is fast transition. So if I change the input here, at the same time very fast output should change or make transitions. But if we have a load capacitance like that, that will actually prohibit us to do that. It will take some time to change from one state to another state. So basically the idea is what generally happens. So let's say maybe the inputs we have are all 5 volts. Okay, sorry, color should be changed. So this is 5 volt, this is also 5 volt, this is also 5 volt. We know this will be all will be reverse biased, and because of that this is forward biased, this is in saturation, this is in saturation. So at the output we are going to get what now? 0.2 volt, right? Now suddenly if you change one of the inputs to 0.2 volt, let's say if I just remove that, change that to 0.2, what will happen? This value will now go to 0.9 volt. As a result, this will be cut off, this will be cut off, this will be cut off. And now because of that, this is turned off. This is practically open circuit. Now if this circuit is open circuit and also a capacitor is connected here, it should, the voltage at the output should move to 5 volt instantaneously. But because we have this capacitor and across a capacitor, voltage cannot change abruptly. So gradually it will move from 0.2 to 5 volt. And what will happen? Current will flow through this path like that to this capacitor to charge it up and make this voltage from 0.2 to 5 volt. But the time it will take for that to happen, for making that happen, is governed by this capacitance and this resistance. And we actually multiply these two, which is called RC constant. Okay. So the time that will be taken for this charge up is proportional to this RC constant. Actually, if I want to be very accurate, like approximately 5 multiplied with the RC constant we have, that is the amount of time actually be taken by this uh, capacitor to get charged up to this value. So you can understand there will be some delay, right? And if we can also reduce this resistance value so that this time is reduced. Okay, but the problem is, if you do that, whenever this transistor is actually turned on, previously, just in the previous state, we saw that this was saturated. As a result, this path was closed and current can actually flow through this path. In that moment, if you reduce the value of this resistance, high amount of current can flow through this path, wastage of current, as well as that can also damage the transistor itself. So not a good idea. So what you have to understand, this circuit actually this portion, the two things we have, the transistor at the bottom and resistance at the top, they have specific purpose here. The transistor, whenever turned on or in saturation, it tries to pull the output down to 0.2 volt or pull down it, right? So this portion is called pull down circuit, and whenever we need the output to be high, this particular resistance connected with 5 volt tries to pull the voltage up. So this circuit is called pull up circuit. Okay, so always you will see this kind of configuration. Even whenever we will talk about CMOS circuit, you will see that there is a pull down and pull up portion of the circuit. One portion tries to pull the circuit up to 5 volt, output to 5 volt. Another portion tries to pull the output down to 0 volt or close to that. That is the idea. So here, as we have used a passive resistance here, these are called passive pull up, and this is used by this is actually using a active device, transistor. So this is called active pull up, pull down, actually, because this is pulling down. So this is what we can explain. So the problem is, using this kind of passive pull up, we are having this kind of problem, that it is taking much more time to charge up, or this kind of load capacitance is causing us to get more delay at the output. So how can we solve that? To solve that, we are going to use a configuration that looks something like this. So instead of that one resistance, what we have connected here, a transistor Q4, a diode, and also one resistance is also connected here. Now this kind of circuits, this is called totem pole configuration. The reason of this name is because three different components are stacked on top of each other, kind of like totem pole. You can search what is totem pole in the internet, you will understand. So they are also stacked one after another, something like that. So how it actually helps, we will try to understand now in this circuit. Okay, so again, here we will start with a condition whenever the inputs are 5 volt, 5 volt, 5 volt, all of the inputs are 5 volt, and then these three junctions are reverse biased, and we need 2.3 volt for these two transistors to be turned on, and as a result, at this point we are getting 2.3 volt. That is confirmed, right? Now in this case, because this particular transistor Q3 is in saturation and at the output we should be getting 0.2, now ideally we want this Q4 to be turned off right now. Okay, let us try to actually examine whether that is correct or not. So what we will do is try to find out what is the voltage we are getting at this point. Okay, so first of all, let us give some names to all of the nodes. That will be easier to understand. Like this portion can be called as what? Maybe I can use this color. So let us call that P3. This is E3. This is what? This is C2, as well as here we can also say this is B4 because base of Q4. Similarly here this can be said as C4, this can be said as E4. This is what? This is actually C3. This can also be said as what? E2, and this is B2. I'm just giving some names to the nodes so that we can explain easily. Okay, so the idea is we have to find out the node voltage here. So that means C2 voltage or B4 voltage, whatever. So they are same value. So you know that because currently this Q3 is in saturation, so B3 should be 0.8, right? B3 should be 0.8, and Q2 is in saturation, so from C2 to E2 the voltage difference should be 0.2, just from collector to emitter of Q2, that is 0.2 because this Q2 is in saturation. So C2 should be what? This voltage here plus the voltage here. So from here to here total voltage is C1 is equal to 1 volt, right? Or also we can say V4 is equal to 1 volt. Same thing. We can remove that as long as you can understand. So now we have to look at the voltage here B4 and try to understand whether that is enough to make this path, turned on. That is the idea. Make this path turned on. We know already this is turned on, but whether this particular path can be turned on or not, that is the idea. So for that we need at least 0.7 here for this junction. For this diode to turn on we need at least 0.7. So 0.7 plus 0.7 here, and already we have 0.2 here. From the saturation condition we know that already we have 0.2, so 0.2. So 1.6 volt is required at B4 if I want Q4 to be turned on and also this diode to turn on. So which is not possible. As a result, this particular diode, particular transistor Q4 will be turned off whenever all of the inputs are high, and at the output we are getting what? 0.2 volt at that moment. So because capacitor is here, that amount of voltage is charged here and capacitor is getting 0.2, so V0 is equal to 0.2 right now, and because of capacitor the voltage cannot change abruptly. Okay, so now what we will do, we will try to change the input and look at the circuit how it behaves. So let's say suddenly I change one of the inputs to 0.2, right? So if that is the case, then obviously then one of the junctions will be forward biased, and as a result the P voltage, VP voltage at node P will be 0.9, right? If that is the case, then that will not be enough to keep this Q2 and Q3 saturated, right? So Q2 will be cut off, Q3 will also be cut off. So in this path you can see that the C2 node or B4 node is now not tied to this Q2. So the value of C2 can be changed to any value or can go higher up to provide for Q4 and E4. That's the idea, because these are now turned off. But still you have to understand, because we have a capacitor, suddenly abruptly the voltage we got earlier 0.2 at C3 or at the output cannot change. It's still 0.2, but these two are now kind of turned off. So now we have to again recalculate what should be the value of voltage at C2 or B4. So how can we calculate? Now B4 will provide the amount of voltage required for these to get saturated and these to be turned on, and whatever voltage we have here, right? Because this path, through this path current will flow, right? So for that we need 0.8 here if I want to make Q4 to be saturated. So for Q4 we can say VBE Q4 set is equal to 0.8. For the diode, let us call that VD. VD is equal to what? 0.7 we need. And we already know C3. This node is currently at 0.2 volt because voltage cannot change abruptly. Still, across our output, we have 0.2. So, V naught is equal to 0.2. So, we have to add all of them, right? And finally, what we get? 0.8 plus 0.7 plus 0.2, which is equal to what? 1.7 volt. So 1.7 volt we are going to get at V4, which will make Q4 saturated. Diode will be conducting, and as a result, now this transistor is in saturation and current can flow from here to this path like that to there. Okay, from here to here like that. Okay, and that will make capacitor to get charged, and the voltage here, which was 0.2, it will keep increasing from 0.2 to 0.3 to 0.4 as it gets charged up. Okay, now the issue is, as this voltage is increasing, the voltage at this node B4 should also increase as well, because initially when it started, for everything to make sense, the voltage at B4 had to be 1.5 volt higher than C3. You see, 0.2 and 1.7. Because of that, this particular junction was forward biased and made this Q4 saturated. This diode was turned on. So if this voltage increases to a higher value, let's say 0.4 or 0.5, it has to be 1.5 volt higher than that. So as it will get charged up, the voltage at C3 will increase. To keep this one saturated and to keep this diode turned on, B4 has to increase. B4 has to increase, but up to how much it can increase? So it will happen that it will get charged up and up, but as a result, it will get increased as well. But up to how much? Because if this node voltage increases, that will reduce the current going through this path, obviously. And also, whenever B4 reaches 5 volt, at that moment, if B4 becomes 5 volt because of C3 increasing, at that moment no current will go through the base current will be 0, right? So at that moment this capacitor will be fully charged, and that voltage is what? That voltage is basically slightly lower than 5 volt. We have to calculate, we will calculate, but that is how it will happen. So the capacitor will get charged up, the C3 value will increase, as a result B4 should also increase, but that will reduce the current, base current going through that. So if base current reduces, collector current will reduce as well, right? And from saturation to active to cutoff, in this way this transistor will move on to different modes and finally go on to cutoff mode. Okay, so whenever that happens, I mean whenever there is no current flow through this path, that moment this diode will be turned off, and also this junction will not be getting the amount of voltage that it requires to be at least active. So that bare minimum voltage we will try to calculate now. So if this diode needs to be forward biased, it needs 0.7 volt, and we know whenever we have 0.5 volt across a diode, that is called the cut-in voltage. That is the maximum voltage up to which diode doesn't conduct, and after that diode starts to conduct. So this will be the maximum voltage whenever there will be no current through the diode, right? And for the transistor from base to emitter volt, if we have 0.7, it's in active mode. So slightly lower than that is 0.6, right? This is the maximum voltage we can have across this base to emitter junction of Q4 until it starts to conduct. Okay, so this is the amount of voltage we will have from here to here, and we already know at that moment B4 will be at 5 volt. So 5 volt minus this amount of voltage will be the output voltage, or the maximum voltage up to which capacitor will get charged to. So this value is what? 3.9 volt. Okay, so because at that moment diode will not get enough voltage to turn on, because it is getting only 0.5 volt. This junction will not get forward bias because it is getting 0.6, not enough to get turned on, and B4 is at the maximum voltage it can be, so that this current is 0, 5 volt. So 5 minus this reduction of voltages, then finally we get the maximum amount of voltage up to which the capacitor can get charged to. Okay, so now the idea is, why this is important, because now whenever it was getting charged through this path from 0.2 volt to 5 volt, that situation, the amount of time required can be calculated through this equation, which is 100, the resistance here. Then whenever in saturation, what is the resistance we can, find through this path for this particular Q4. So let us call that RSQ4, saturation resistance. And what is the diode resistance? It is also a dynamic value, but still we will take a static value to make everything easier. Let us call that RF. Okay, and actually compared to normal resistances, these values are very minuscule amount of resistance. So this is the total resistance multiplied with the capacitance CL. So this value will be much lower compared to the one we calculated previously. Okay, so as a result, it will quickly get charged up to 5 volt, and because of that, we will see that this transition will go much faster compared to the previous circuit we had. So this is the improvement we are discussing. That's all for this lecture. Thank you.